All right. Hi. So we did our 456 final project on an AlexNet implementation for a fish classification data set from a fish market. Initially, actually, we wanted to implement a segmentation or object detection algorithm like UNet or RCNN, for example, on images that we took of the fish in the Hubble aquarium. But we realized afterward that the pre-processing that we would need to do on those images would be too daunting and too time-consuming a task. So that's when we pivoted to AlexNet and the fish classification data set from the fish market. But before we actually jump into our project or AlexNet, we would just like to go over what we attempted with the aquarium set.
All right. So this is a frame from the video that I took in our aquarium. And our attempt to isolate the fish was to select a frame and subtract the average of set of frames around this certain frame. And this is what we get. So you can see that we can clearly see the fish around. However, there's a lot of details about the corals. That's really hard to actually separate out the fish alone. So now let's get into the AlexNet implementation in our project.
All right. So now that we pivoted to AlexNet, that's the code we have here. So before actually implementing or running our algorithm, we had to do image preprocessing and pipelining. This is the first time I think that any of us have worked with a data set that wasn't prepackaged into TensorFlow. Like for example, the SciFar10 data set from mini project 2 was included in TensorFlow. But because we have external images, we had to do preprocessing and pipelining. So we actually had to create this data frame that included the file paths of each of the images along with their respective labels. And when we format the data frame as such, quick interlude, this is what the fish image looks like. But when we format the image, or format the data frame as such, rather, we can utilize an image data generator object from TensorFlow or from Keras particularly. And within this object, there is a flow from data frame method, which handles the creation of the training, testing, and validation sets. So it reads all the data frame information, it reads the file paths of the images, and actually creates the image sets for training, testing, and validation. And we also were able to specify the batch size. So we did batch learning with size 32. And we were also able to specify the target size of 227 by 227, which is basically the downsampled image from the initial size of, on the order of 1,000 pixels by 1,000 pixels. And this 227 by 227 is in particular important to AlexNet. But yeah, now that we were able to cover the pipeline and pre-processing, we can move on to our AlexNet implementation.
Yeah, so hi, my name is Alex, and I'm now going to talk about how we investigated, implemented, and modified the architecture of the AlexNet, as you can see on the screen. So AlexNet is an image classification architecture. It won the 2012 ImageNet Challenge, and its key to its success was the ReLU activation function, one of the first architectures to use ReLU, and ReLU is everywhere today in neural networks. And the network architecture is rather complex. So the AlexNet architecture consists of 5 convolutional layers, 3 max pooling layers, 2 normalization layers, 2 fully connected layers, and 1 softmax layer. Each convolutional layer consists of convolutional filters and a nonlinear activation function ReLU. But pooling layers are used to perform max pooling, and the 2 fully connected layers have trouble, meaning that a rarely subset of their neurons are turned off during their training, and this is done to prevent overfitting. Our AlexNet architecture has around 58 million parameters. Initially, we were concerned about overfitting. As we mentioned, there are so many trainable parameters for only the 9 classes that we did, we thought the network might pick up on the image specific details like the orientation of a fish or the background. Unlimitedly, there's no significantly overfitting, in which we were pleased with. Also, the original AlexNet architecture takes in the 227 by 227 image as an input. In our application, we had to use a 227 by 227 downsamples of the initial fish images as input. The image then passed through 2 convolutional max pooling layers, followed by 3 convolutional layers, followed by 2 fully connected layers, and each with 4,996 layers. And now Sal's going to talk about the plots that were created from our AlexNet architecture.
Yeah. So as you can see, like these are the loss and accuracy graph of our AlexNet architecture. So from the second graph, the training validation accuracy, you can see like the training metrics are ultimately better than the validation accuracy, and you can see like the validation accuracy are pretty horizontal, and there's no clear sign of overfitting. And more interesting is like in the first few epochs, you can see like the validation accuracy is like higher than the training accuracy, and this might be because of the dropouts. So like we turn off some of the neurons to avoid overfitting, and eventually we'll turn back on to get a more robust network. And now let's go to confusion matrix.
Yeah, just really quickly before we go to the confusion matrix. So yeah, when we turn on the neurons when doing validation, which creates a more robust network, which is a potential reason for why the validation accuracy is higher than the test or training accuracy in the initial epochs.
All right, and now we're going to explain the confusion matrix. So the confusion matrix shows that our network was able to successfully clarify all the 9 fish species. Interestingly, there were multiple gill-headed bream classified as sea bass, but there were no sea bass classified as gill-headed bream. This is due to it being a possibility that the sea bass having different features than the bream does not have. It's also interesting to point out that the red mullet precision is 1, which means none of the other fish species were misclassified as a red mullet. And now Ankit is going to talk about the prediction images and going to wrap up.
Yeah, yeah. So just to clarify, here's the precision and recall plot, and yeah, yeah. So again, just as a quick clarification, only one of the sea bass images was classified as a gilt-headed bream, as you can see here. But yeah, moving on to our final image, similarly to what we had to present in mini project 2, we randomly sampled 9 test images and returned their predicted class, their true class, and their probabilities, their classification probabilities. So you can see here is that, there's a selection of images. Incidentally, all 9 of which were classified correctly. But what we see is that, while most of the images have very high classification probabilities, classifying them as their, as whatever species the network does, we see classification probabilities of 99%, 98%, almost, certain probabilities. We do see a few of them that are very low. Like, for example, this red mullet, the network only provided a probability that it is a red mullet of 39%. But this 39% is the highest classification probability out of any of the 9 species. And I think it just goes to show that the network is not necessarily always confident in its decisions, but it still has to make a decision. So yeah, ultimately, I think from this project, we would say that we successfully implemented AlexNet. And I think going forward, we'd like to explore more nets like detection and segmentation architectures such as RCNN or UNet, and perhaps using our additional knowledge, we can come back to the aquarium idea and the aquarium project at a later date. So yeah, thanks for listening, and thank you for a great semester.